So this is some work I've done funded by the National Science Foundation to get lessons learned from failures and share those. And this is a definition of structural engineering you might have seen before. It's also been used with geotechnical engineering. But basically, and then to talk about failures is to talk about a failure being an unacceptable difference between expected and observed performance, not necessarily a full collapse, but it can involve functional failures as well as collapses. Can you all see the slides reasonably well enough to continue this way? Okay.
We can see the edited version of your slides. Yeah.
Okay. Yeah, I'm really not sure why I've got a new computer, so maybe it's just why the presentation is not working so well.
Yeah, you can just proceed. Otherwise, you could disconnect your external display and then it should work. But
yeah, okay. So a lot of what I've worked towards is what I'd refer to as failure literacy, which is developing this among engineers and engineering students. And I define failure literacy as having a knowledge of well-known failure case histories, understanding causes behind failures. What's really important is recognizing patterns of repeated failures that occur again and again. There is a role of failure in the development of design procedures and codes, and also developing a certain level of skepticism. And there's a very long definition of from the ABET accreditation of what engineering design is that we're required to teach our students, prepare our students to do. But this is my simplified version of design, is that you anticipate everything that can possibly go wrong, and then you make sure that it doesn't happen. But the tough part of that is actually figuring out, number one is figuring out those things that can go wrong, because it depends on your ability to visualize these, to visualize problems. Specific to concrete and concrete structures, there are a number of very important case studies in concrete structures. Willow Island Cooling Tower, which is really about formwork. The Air Force warehouse collapses of 55 and 56 that made their way into the codes in terms of shear reinforcement. And then a series over about 10 years of punching shear collapses of structures, starting with 2000 Commonwealth Avenue. Some other important cases, and I probably won't have time to get into these today, looks into building performance under extreme conditions. And that includes the Ronan Point collapse of 1968, as well as the Oklahoma City bombing, not far from where I live now in Stillwater and Pentagon. And then also looking at reinforcement, strut and tie models, development, continuity of reinforcement, the autoroute de la Concorde overpass collapse in Laval, Quebec, about 14 years ago. So I think Charles maybe showed some construction of cooling towers in his presentation. And this is the Willow Island cooling tower collapse, where the formwork and the workers, 51 workers, unfortunately all fell down inside the tower, killed 51 workers, and it was a progressive collapse of the formwork. This particular case was a couple of natural draft hyperbolic cooling towers. And I've been told that the workers were actually really kind of locals, mostly farmers from the area, and they were paid by the day depending on how long the day went. And so they were kind of, they had an incentive to rush the work. And this is an illustration of the typical cooling tower in dimension, very large structure. And it had used a patented lift form system that had been used for 36 cooling towers. It was a jump form system and kind of a sliding system, somewhat related to the first system that we saw this morning in today's first presentation. a lot of different components. And then this diagram shows it where you can see the yellow is kind of the jump form system. And you can see that the two pieces of form slide or jump past each other up the tower. And then you have the various days lifts of concrete that are holding the tower in place. This is in basically into 4 levels of concrete. So the bottom part of the formwork, at least in theory, would be in well-cured concrete. So it covered 4 levels, but is supported entirely by the previously completed part of the tower. And they did a 5-foot lift every day, at which point I guess they could go home, and the system was then jacked to a new elevation, and the concrete was delivered up by a hoist system. So at lift 29, 170 feet in the air, there was the lift collapse and 51 workers were killed. Very rapid, in about 20 or 30 seconds. And it's been pointed out that a later version of this form, actually, they were not all connected together. But in this case, because everything was continuous, it tended to, the part of the form that collapsed pulled the entire rest of the form around the cooling tower. National Bureau of Standards, what's now NIST, in those days would do investigations for OSHA, and they wrote a report, and they found that they basically, like any forensic investigation, is you look at all the possibilities, and then you eliminate the possibilities as you go. And they came that the forms are held in by bolts. They did not think that the bolt failure was likely. Their finding was that the strength had been compromised by cold weather, and they had gone through a relatively cold period, highs in the 60s, lows in the 30s at night, and the concrete compressive strength was estimated only to be about 220 psi. So that was their finding on the tower. And they eliminated the concrete bucket impact, cables, braking as a trigger. And it was actually a fairly early use of finite element analysis to try to determine the strengths. And they concluded that the construction loads were imposed before it had enough strength. There was another investigation done by Lev Zetlin Associates, it's LZA, and they said that the concrete strength really didn't have anything to do with it. It was premature removal of anchor bolts from the early portion of lift 27. And I think they're the ones that pointed out that that the workers had an incentive each day to complete work as quickly as they could. And another NBS report then reviewed that and looked at the effects of the bolts and the location of the static line. But I think they kind of held with concrete strength as being the issue. They found that even the missing bolts would have reduced the stresses, but it still exceeded the capacity. OSHA issued 10 willful citations and 6 serious citations, failing to test lab cured specimens before removing forms, and lack of procedures on the site, and also cited the lab and the concrete supplier. But in fact, OSHA came under some criticism as well for not having sufficient safety inspectors, only 7 in all of West Virginia at the time. And as a result, that led to some changes in responsibility for formwork as adapted by OSHA. Moving into one of the first ones that I actually got interested when I was a graduate student at MIT in the mid 80s, one of our courses looked at this collapse of 2000 Commonwealth Avenue in Boston, which was an apartment building under construction. And it was a flat plate, which is a common building type with punching shear as a critical failure mode. And interestingly, in the years of teaching reinforced concrete, we don't really talk that much about these building types. And sometimes we really don't even get to punching shear in the first undergraduate course. Again, a common theme is that cold weather um, inhibited the strength development of the concrete, which in this case was fairly poor quality, and the fresh slabs were overloaded, and this particular collapse killed 4 workers. So this actually shows the extent of the collapse, where the shaded area represents the extent of the collapse. And here are some photos from the Boston Globe. You should not be able to see the elevator core from the outside of the building. And again, a classic illustration of the punching shear mechanism. Um, one of the reasons we study these failures is to try to disseminate the results and to improve knowledge of the collapses and their effects. And in this case, there was a report written for the city of Boston. And the conclusion of the report said that the information of this collapse should be widely disseminated. And I think there's only one copy, which is in the Boston Public Library. So a student and I later wrote a paper about this, and this is also included in my book that I wrote about cases. About 2 years later, we had the classic collapse of Bailey's Crossroads in Northern Virginia. Again, this killed 14 workers and 34 were injured. This was also investigated by the National Bureau of Standards. I have to credit Nick Carino, who many of you will know from ACI, who provided me with many of these NBS photos. And this is also a punching shear failure. So this is actually not supposed to be 2 buildings. It's supposed to be a single building, and the middle part of the building collapsed all the way to the ground. Another view also shows the demolished parking garage that fell apart in the progressive collapse. This is actually the photo I ended up using for my book cover. It's interesting that in this case, there was an aerial photograph taken just before the collapse showing the 4-day sequence of construction, 1, 2, 3, 4, and the red lines outline the collapse section. And one of the earliest hypotheses of this collapse was that the crane that's kind of in the middle had collapsed and come down through the building. In fact, what the investigation showed is it was the building collapsing out from under the crane that brought the crane down. The NBS found that it was premature removal of shoring and insufficient concrete strength, estimated only about 1,000, 1,500 PSI. What is kind of scary from a structural engineering standpoint is that anytime there is a failure, and particularly with loss of life, they cast a wide net in finding responsibility and issuing fines, and the structural engineers and architects were held responsible even though the design was adequate. Collapse was due to poor construction practice and in fact not following the procedures. On the other hand, a collapse that we can directly attribute to issues of design is the Harbor K condominium, another similar collapse in Cocoa Beach, Florida, March 27, 1981. This was another punching shear failure. Interesting thing about this case, and you may or may not be aware that after 46 years, the American Society of Civil Engineers in October published the first new total rewrite and revamping of their code of ethics. And the code of ethics of ASCE, and actually the previous one as well, and in most states, say that you're supposed to work within your area of competence. So this raises the issue of whether or not they holding licenses, but working your entire career for NASA, does that in fact qualify you to design reinforced concrete buildings? This is a comparatively low-rise building, and this photo and some of the annotations basically show the direction of concrete placement and the direction of construction at the 5th floor of the building. which for all intents and purposes was held up by the formwork. And that was, in the case of Bailey's Crossroads, it was premature removal of some reshores. And because the building was so tall, you had formwork and reshoring over several levels. But in this case, the formwork went all the way to the ground, but once it was removed, the building collapsed in all that was left as the elevator towers. Um, this shows the flying formwork system that was used, and you can see the top level and then one a little bit to that one that's hanging from the crane. So those could be moved up, and then you had reshores put together, and the reshores in this case for a 5-story building went all the way to the ground. And when the NBS investigated, they found that at the time of collapse, the first floor reshores had been removed, and at that point, the building was totally unable to sustain its own weight. And here is the wreckage showing one of the flying form systems in and among the columns. This photo shows both the slabs after the collapse, how they've piled up on each other, but also the telltale sign of a punching shear failure where the slab ripped away from the column. So what went wrong with the design? Well, as it turns out, just about everything that you can do wrong. The slabs were very thin, and in part that was there were no checks made for deflection or minimum slab thickness. There were, in fact, no checks made in the file for the punching shear. Also, the column reinforcement spacing. So if you look back, those columns look very thin for a building of that nature, but they're also very heavily reinforced to the point where you almost could not get the concrete into them. And there was no calculation of the effective depth of the slab flexural reinforcement. And to compound the problem, the chairs, even though the slab is only 8 inches thick, the chairs supplied, structural drawing had chairs that had a D of 6.3 inches, but in fact the chairs were an inch shorter than that, which further reduced the capacity. So when you look at your standard calculations for computing the punching shear capacity of a slab, it depends on the dimensions of the column as well as on the effective depth of the slab. And you can see that all these errors making the columns too small on the one hand, and having the slab be too thin, and then having the effective depth of the slab even thinner with that, all of those really reduce your punching shear capacity to the point where the building cannot hold itself even under the dead load. So that basically showed the area where it's believed that the collapse started, and then it spread in all the different directions. So so it really came down to insufficient punching shear capacity, the no punching shear check being made during the design of the floor slab, and the incorrect placement of the top steel that further reduces that punching shear capacity. So one way of looking at this is that structural engineering is definitely not rocket science. It seems to be a whole lot more difficult than rocket science. The two engineers did lose their licenses, but the practice of engineering in most states to this day is mostly self-regulated. If you have a PE and you think you're able to do something, then in that case, they felt that they could design a reinforced concrete building, despite the fact that it was totally different to the engineering practice that they've been doing throughout their careers. I believe one of the contributing factors at this time was because there was a building boom along that coast of Florida, that had the structural engineers were in short supply, and so it made it more lucrative for people to want to work in that area. This is an interesting this one from 14 years ago, and there's a great report that was issued by the province of Quebec. It's interesting when you talk about Quebec bridge collapse, you have to clarify whether you're talking about this particular bridge collapse or the very famous steel bridge collapse of 1907. This is, of course, the more modern one, since we're talking about concrete structures today. This is the structural the part that is collapsed was a span of pre-stressed box beams, and the part that stays up is also box beams, and then you can see the lines that are essentially supporting the box beams. So it was designed and built often, particularly when you have a common Department of Transportation type of building. A lot of these would be designed and built at approximately the same time. This side-by-side pre-stressed box girders, and they rested on cantilevers at each end, and they happen to coincide with the expansion joints. And what you end up when you do that, of course, is you have a relatively complex load transfer. As you saw this morning in the first presentation, we saw a very complicated load path, but so this is not quite that complicated, but it's still a problem. But to have that point also be at the expansion joints, that made it difficult to seal and maintain. And I don't know how many bridges of this type there were in the area. It seems like it was not a terribly common one. But what is kind of interesting is that there was a substantial repair project that took place in 1992. And it was possible that in the course of repairing the bridge at that time, they actually did some level of damage that played into the subsequent collapse. This is also, as you could see in the first slide, this is also a skewed bridge, which leads us to various additional complexities of load transfer. But you had a longitudinal joint that separates the two traffic directions of the bridge. And then at each end of the bridge, you have an expansion joint, and it's supposed to account for 90 feet of expansion, but it also provides for load transfer. And how did it do that? So go back a little bit to this picture. If you look at these ends, you see these look like fairly solid abutments, but in fact, they're not. That's just a wall. And the main structure of the abutment is a overhanging beam on a diagonal support column. And the left and right sides outside of the expansion joints are cast in place concrete. And then those 90-foot box girders that we're looking at from the side are pre-stressed concrete. And the connection is made by basically a DAP cutout of the pre-stressed concrete beam sitting on a ledge in the reinforced concrete. And before the 1992 repairs, after about 31 years of service, it wasn't looking really good. If you look at the two ends at the expansion joints, and if you think about what happens with an expansion joint, is that the part on the right of the top figure and the left of the lower figure is the pre-stressed, and then you have the supports, and you can see that that concrete looks deteriorated. You've got a parallel crack. all not looking extremely healthy. And not only does that have to support the vertical load of the end of the box beam, but as that expands and contracts, it's going to have a tendency to also apply some tension and some prying and to pull apart those. So clearly those supports are a point of weakness. Um, this collapse September 30th, 2006. 5 people were killed and 6 people were injured. Of course, um, when you have a bridge collapse like this, if you're unlucky enough to be under the bridge at the time, your chances of survival are very small, and that's what happened. There was a small period of warning in that puddles of water and chunks of concrete were observed, but not in, there weren't any measures taken to close the bridge. Whether that was possible, it's hard to say. And also some drivers noted bumps across the expansion joint. So as they were driving across the bridge, they noticed that where the expansion joint should be level, they were in fact experiencing some bumps. And this is taken just before the collapse. And the mechanism of the collapse is that that concrete support essentially peeled downward and dropped all of those box beams onto the roadway and unfortunately onto some vehicles. So now, looking at our load transfer mechanism, you can see the load applied to the, would be applied to the end of that cantilever, and it's pretty deep, and you have a purple hairpin bar to hold that in place, and then a yellow diagonal bar that then would overlap with the number 14 top bars because that part is in tension. And so that would be your load path. And in 3 dimensions, this is how it would look. And one question is, even if it's built perfectly, is that length of the large bar, the red bar, enough to properly develop that? And is that length of the yellow bar where it overlaps enough to provide proper load transfer? So in my basic reinforced concrete class, we would calculate some development and transfer lengths, these type of bars, and compare them to what was actually done. And then this is actually what you had in the field, because it's actually, there's a lot of steel there and it's kind of tough to get it all to come together. And then as designed and as built, what you actually end up with is that yellow bar really doesn't overlap with the red bar at all. And what you end up with, if you draw a line just below that red bar, you can essentially get one plane of completely unreinforced concrete that's holding the bridge up. There was also a lot of work done in the report on materials aspects of this. So the top bars weren't really anchored and then really not properly installed to the plans. And then there was some confusion about the specification and the quality of the concrete that should have been used for the abutments, and not particularly resistant to freezing and thawing, which in Quebec, you would obviously want resistance to freezing and thawing. What's a little hard to figure out is what caused the crack to form and spread on that day, what caused the triggering mechanism. You can also look at this from the standpoint of analyzing it from a strut and tie model. And this came out of, again, from the investigation report of how you then have your ties in tension to carry the force. But you see that that diagonal tie has got to somehow connect and transfer force to that top horizontal large bar if you're going to provide that strength. And so there was some laboratory tests carried out at McGill University looking at both as designed and as built. I think actually, if you look in the investigation paper, the as built actually held more load than the as designed, which is kind of bizarre, but it was much, much less ductile, which is of course a problem. And then in the post-mortem looking in, you can kind of see that we have some problems of concrete quality, but you also see that you've got a fairly extreme top bar effect with those number 14s, where essentially the bottom of the bar doesn't even look like it's buried in the concrete. So here, closer look of the collapse, how the up at the upper left, that part peeled away, dropped that entire roadway, and unfortunately onto some vehicles, and then some vehicles on top, but you had a better chance of survival as well. So not really going to talk about this because other than the NTSB report that's been published, there's still, I think, some ongoing investigations and so forth of FIU pedestrian bridge collapse. What's really unfortunate about studying failures is that you have new material all the time. And I think there are a number of people, now that the NTSB report is out, there is a group from the American Society of Civil Engineers Forensic Engineering Division that's taking another look at that. And I've been working with the ACI Committee 133 Disaster Reconnaissance to try to figure out if there's anything to be learned from this. Because what you find when you look at these cases is you often find one of two things. Number one, is our standard engineering codes, procedures should have been adequate to prevent the collapse, but they weren't correctly applied, which means that we don't necessarily need to change codes, but we do need to maybe pay attention to how things are done. But sometimes, as with the Air Force warehouses of 1955 and 56 and some of these other cases, we find that our current codes are not adequate and we need to go back and take a look at them and maybe make some adjustments. And so one of the reasons that going forward, we're going to want to look at this case is to see if there is anything in the code that needs to be done differently. So as I begin to run out of time, much of which I lost by trying to fumble with I don't know, maybe new version of Zoom. There's a lot of causes. Failures have technical causes. Sometimes they're innovative systems. Sometimes they're forgotten mechanisms. Sometimes it's a matter of pushing the envelope. I mean, codes and procedures are developed based on the body of knowledge of the research base and the structures we've built. And when we do something differently, sometimes we're going outside of that database. Or communications, disconnects between the designer, builder, and the inspector. There are some allegations looking at the NTSB report that there were some disconnects on the FIU bridge collapse. And you have issues of maintenance and operations. You also have issues of materials and deterioration. I think we can learn from each individual failure. What's really important is that we learn from patterns of failure as we move forward. If you have an interest in this and other cases, my book Beyond Failure, published by ASCE back in 2007, is available. And as I said, I received some grants from the National Science Foundation, first of all, to look at case studies and then to look at how we could incorporate them in the education of civil engineering undergraduates, and also how we can document the impact of that. And I do want to thank NBS NIST and the photos provided by Dr. Nick Carino and the Forensic Engineering Division. I think I have a question in Q&A. Were the Bailey's Crossroads architects and engineers able to appeal the judgment against them? That's a good question. I honestly don't know. It's been a while since I put that together. It's possible that I covered in my book what the eventual outcome was. I think they did try to appeal. Got some things in chat. Okay, looks like the next speaker maybe is having. Anybody have any more questions you want to throw out in Q&A or?
There is one question: are you aware of any punching shears in projects where stud rails were utilized?
I have not come across one, no. And in fact, when I talk about punching shear in the class, I generally will refer to those as an alternative. I think as a possible alternative for dealing with that. But no, I've not come across any that use the stud rails. Fortunately, I think the latest one I looked at, as I said, was 1981. So it may be that we started to pay a little bit more attention. The ASC Technical Council of Forensic Engineering, what's now called the Forensic Engineering Division, was actually formed in the mid 80s after a lot of failures that occurred in the 70s and 80s, specifically to disseminate information on them and to try to handle some of these issues. Any other questions? I don't see there's any more in chat.
No, I know that that you have done some excellent work in looking at various failures and turning them into educational topics, and I think that that's very important. If you read the NTSB report on FIU, it does appear that the concept that we all talk about in our first class of that we design the structure so that it will tell you it's falling down before it does so, may be something that's worth looking into. It looks like Jeff has had his technical problems addressed, so I'm going to turn things over to the next moderator, but not before I say thank you so much for the presentation.